next test is coming up on Wednesday, so I thought that we could do some just reviewing overall today.
Okay, good. You have some review material?
Yeah, so it's on Chapter 8, and she assigned us to do pages 524, 525, and 526 up to number 35.
Did we figure out that we had the same books exactly?
Yeah, we did.
Okay, so I'm on page 524. Where do you want to start?
I figured that we could probably just go over like one of each. I'm pretty comfortable with like the logarithmic functions and stuff like that. I just have a lot of trouble with graphing mostly.
Okay.
And then a little bit of difficulty with like exponential growth and decay difference.
Okay.
And just like that. But yeah.
Well, the best way to clear up those kind of difficulties is to find a problem that you wouldn't know how to do, and then let's do it.
All right.
I'm looking at the problems that on those pages, and I don't know that I can just start anywhere and go from there. The chapter test is never a bad place to start.
Okay.
That's on 527. What'd your teacher say? 524, 525, and 526?
Yeah.
Well, let's stick to those pages then.
All right.
Let's start with 1, unless you know of a better place to start.
I haven't heard of one yet.
Huh?
All right. So just y equals -2 to the x plus 4?
Yeah. So what you have to know to be able to graph this function is what's the parent function?
Is it, oh gosh, is that the y equals?
In other words, what you're looking at is one of your 10 elementary functions transformed with inflections and shifts and things like that. Remember your transformation section? Well, those transformations apply to exponential functions and logarithmic functions also. So you always have to figure out what the parent function is. What is it on that one?
Is it y equals a times b to the x minus h and then plus k?
Well, that would be the general function. But your number 1 says y equals -2 to the x plus 4, correct?
Mm-hmm.
Okay, the parent function is y equal 2 to the x.
Oh, okay.
Okay, and I'll go ahead and graph that. Looks like all exponential functions. In other words, if I showed you this graph, you'd be hard-pressed to say, is that y equal 2 to the x, or 10 to the x, or e to the x? The only thing you would know is that the base was greater than 1.
Okay.
If the base is between 0 and 1, then it's going to look like this. It's going to be decay.
All right.
In other words, the red might be y equals 1/2 to the x. That half is between 0 and 1, so as x gets bigger, that gets smaller. And a decaying function instead of a growing function. But let's not pertain ourselves to that at the moment. Let's get back to, they want you to graph the function and state the domain and range.
Right.
Well, there's 2 things being done to this function. What are they?
It's getting shifted up 4 and then flipped over the y-axis?
Flipped over the x-axis.
The x-axis.
Remember your transformations. Everything that is outside the function is a vertical transformation. Everything that is inside the function is a horizontal transformation. Well, when I stick a negative sign in front of there, that's outside the function. If I wanted to put the negative sign in front of the x, now that's inside the function. And I call this a vertical reflection because it fits with all the other rules for transformations. In other words, all things outside the function are vertical, all things inside the function are horizontal. So this is a vertical reflection, and that means a reflection over the x-axis.
Right.
Okay, so the very first thing and you have to do your reflections first, always, when you're graphing. If certain kinds of transformations, if you don't do them first, you'll end up with a graph that won't be in the right place.
All right.
If you have two reflections, a vertical and a horizontal, you can do them in either order, but do all reflections before anything else.
Okay.
Now, the next thing we have is +4. What is that?
That means that you are moving the entire graph up 4.
Okay. Without changing its shape, that is a vertical shift.
Yes.
What about the asymptote? In other words, we had an asymptote on the original function that was y equals 0. In other words, as the x-axis goes towards negative infinity, y gets closer and closer to 0. Okay?
Okay.
When you have a vertical shift, well, that moves all your horizontal asymptotes an equal amount. So the new horizontal asymptote is going to be
4.
And let's go ahead and draw it. And notice that the reflected y equal minus 2x, here I should label each of these. I do these one at a time just so you know exactly what is being done. And the black one is y equal 2 to the x. And finally, the green one is going to be looking like this. Same shape as the red, only going towards a new vertical or a new horizontal asymptote. So that's y equal minus 2 to the x plus 4. Now, notice if I would have done the shift first, I would have been in the wrong spot. In other words, if I take the black curve and shift it up 4 and then reflect, I end up way down here below the x-axis with a different vertical asymptote. You know, I might be wrong on that with this particular one. But just always remember to do your reflections first. All right, now let's talk about domain and range. What's the domain of the green line, the green curve?
That's negative infinity to infinity.
Good. The domain on exponential functions is usually all real numbers. The range, however, is not. What's the range on this function?
Is it negative infinity to, or 4 not including 4?
Correct. And so you always want to start from the bottom, go up, and that's a parentheses to indicate up to 4 but not including it.
All right.
All right. Let me look and see. We don't need to do every problem because we won't have time for that. Notice, tell me what transformation is taking place on number 2.
On number 2, it is expanding by 3. So the speed is increasing by 3. Is that how you would say that?
A vertical stretch is what we would call that.
Okay.
Okay. In other words, stretches do change the shape of the curve. And if I'm drawing that, in other words, here's my y equal 2 to the x going through this key point. They all go through 0, 1. But now y equals 3 times 2 to the x means this point has to be 0, 3 that it's going to go through. And that curve would be a vertical stretch, making it appear skinnier. Although with exponentials, it's hard to distinguish even when the shape changes. They all tend to still look the same, but it does go through a different point on the y-axis. Horizontal asymptote's the same. In other words, that vertical stretch does nothing to the horizontal asymptote. It's still y equals 0.
Okay.
Number 3, what two things are being done?
It shifts, well, it has a vertical stretch of 5.
Okay.
And then it shifts to the right 2.
Good. And that's a horizontal shift.
Right.
And notice that all horizontal stuff is inside the function. That -2 is inside the function. It's not outside the function like on number 1. That +4 was outside, therefore it's vertical. That's what I mean by being inside or outside the function.
Okay. Yeah.
Here's an interesting one. I don't know if they get this hard, but what's happening there?
Y equals 2 cube, or to the 3 minus.
What transformation is that?
It would be shifting to the right 3 minus x, right?
Really?
Or like it was shifting down.
Oh, you got it. I'm surprised. I don't know if you accidentally got it or not. First of all, it's not the same as this. Well, it actually is the same as that. Okay.
Okay.
But what transformation is that?
That is, well, that would be shifting to the left.
Right.
Like,
but the way I have to write it is like this. I have to put the negative sign and put parentheses in there. And now that turns into x minus 3. And now this minus sign right here tells you that it's a reflection over the y-axis. It's a horizontal reflection. And when I go to figure out the shift, it turns out that it is actually a shift to the right by 3 units. But notice what I had to do. And this will be the case whether your problem is, you could have a problem that's like that. Okay? Also. And the way I have to write this is, again, I would have to put the negative sign there, and then I would have to make that x minus 3 to be the same. In other words, adding those parentheses changes the sign on that -3, because with the parentheses, the leading negative sign has to be distributed to both. Like I said, I don't know if that was worth the time, because you may or may not get problems this hard.
Okay.
Let me look. Let's look at 5.
5?
Yeah.
Okay.
How can you tell if it's exponential or growth or decay? Go through 5 through 8 real quick. 5 is what?
5, is that decay?
Yep. 6 is what?
Growth.
7 is what?
Growth. No, it's decay.
Yeah, and decay means always getting smaller, okay?
Right.
And if I have 3 times 6 to the negative x, that's the same as 3 divided by 6 to the positive x. And so as x increases, the denominator gets bigger and the whole thing gets smaller. So that's the way you can always figure out whether something is growth or decay. I suppose the other rule is if that's a negative exponent and this is greater than 1, it's going to be decay. If that's a negative exponent and this is between 0 and 1, it's actually going to be growth. In other words, if I had 1/2 to the negative x, that's growth.
Okay. Yeah, because that would mean that the 2 would go on top and be getting
Yeah, that's the same as 2 to the x.
Right. Okay.
Okay.
Yeah, I can see that. Okay.
And in other words, if you look at number 9, if I wanted to know how to graph that, well, same shape as exponential, only it goes this way. Still goes through that same point. Because the reason they all go through that exact point is that when x is 0, when your exponent is 0, your number is 1, always. Any number to the 0th power is 1,
Right. Okay.
including
Yeah.
this one.
0 to the 0 power is 1?
Huh? It's the only way you can say that x to the 0th power is always 1. Because this says that no matter what x is, if I take it to the 0th power, it's equal to 1.
Okay. All right. So,
Looking at which of these look like they might be interesting to talk about.
all right.
On 9, domain is all reals. In fact, I think that the domain is going to be all reals for every problem in this chapter. Range is what on 9?
Range is 0 to infinity, not including 0.
Yeah. Okay. Now let's go to the next page. E. Are you comfortable with E?
I'm actually pretty comfortable with E, yeah.
You are?
But, yeah,
E
the,
approximately 2.718. It's a lot like pi, goes on forever. So the most accurate representation of the number is the Greek letter E. Or rather the letter E, not the Greek letter. That's actually different. That's epsilon.
okay. I get to that one, I think.
So 13, in other words, e to the x, yeah, looks just like 2 to the x. Not going to be much different. I mean, it's close to 2 to the x. It's 2.718 to the x. 1 second, Morgan. Hello? All right, let's see. Yeah, I think you're good on 13 through 16. Let's talk about evaluating logarithmic expressions.
Okay.
For example, log 17, log base 4 of 64. Do these without a calculator.
All right. So, in order to evaluate that, it's like saying how many times does 4 multiply until it becomes 64?
Well, here's the best way, I think, to evaluate a logarithmic expression. Is first of all, make it into an equation. Going to let it equal some number, x, and then we're going to figure out what x is. Now,
Okay.
the best way to solve this for x without a calculator is to turn it into an exponential expression. What is the equivalent exponential expression? And boy, if there's one skill you have to have, it's being able to switch back and forth between exponential expression and log expression. So
All right.
make sure you know how to do that. So what's the exponential expression here?
Is it 4 to the x equals 64?
And now you can see what the answer has to be. What is x?
X is going to be 8, right?
3.
3?
4 cubed.
Oh, yeah. Okay.
Okay? Remember, we're dealing with exponentials here. So it's 4 to what power? Not 4 times some number. That's where you were originally going wrong. So
Yeah.
it's 4 to some power. Now you don't have to add the x and turn it into an equation. Once you get used to working with logs, you can tell that this means 4 to what exponent equals 64. It's just I've always found it easier if you just do this because I know exactly how to translate that into an exponential expression, and then they'll always be easily solved. Now, if they would never give you this problem, because this you can only solve with a calculator.
Yeah.
4 to what exponent equals 63? Well, it's going to be like 3.9437. It's going to be some odd number. So all the ones they're giving you in this book know that they're going to end up being whole numbers as answers. Otherwise, you would require a calculator to do them.
Okay.
So 18.
18.
Mm-hmm.
Log base 2 of 1/8.
Yeah.
Okay, so then that would translate into 2 to the x equals 1/8.
Correct.
So then is that
Does
2
x
to the 1
need to
third?
be positive or negative?
It's going to be
Got to be negative.
negative.
Notice that
So
if x were positive, you're always going to get a number greater than 2. Well, that's not true. Sorry, I take that back. But
so does it have to be to the -3 then?
yeah,
Because 2 to the
yes,
third.
yes. 2 to the -3 is the same as 1 over 2 to the positive 3, which is 1/8.
Awesome.
Okay.
Okay.
And so 19 is what?
19 is log base 3 of 1/9. So would that become 3 to the -2?
Yep. 20.
Alright, so that's log base 6 of 1. So is that
So do the translation.
yeah, so that becomes 6 to the x equals 1. So then would it have to be 1/6?
0.
0. Oh,
Remember
okay.
that principle that any number to the 0th power is equal to 1. Therefore, all logs, regardless of the base, of 1 are 0. In other words,
Okay.
this is a true thing. In other words, if I turn this into, well, it was in a logarithmic expression, but in its original form, it said log base 6 of 1. Well, the log of 1 is automatically 0 regardless of the base because of this principle here.
Yes. All right.
Okay. On 22, what's the 4 doing?
The 4 is that increasing the vertical stretch by?
Is that a vertical or a horizontal transformation?
Horizontal
Because it's inside the function. Notice that on 21, the 3 is outside the function. That makes it a vertical stretch. But on 22, the 4 is inside the function. That makes it what? A horizontal what?
Horizontal stretch?
They go opposite. So numbers greater than 1 that are horizontal are shrinks. Numbers between 0 and 1 are stretches. In other words, this is a shrink horizontally. That would take the log curve, which normally looks like this, and shrink it by a factor of 4, which kind of makes it look like I said, when you change the shapes on these exponential and log curves, it's hard to draw them because it's hard to even figure out what a shrink by a factor of 4 is going to do. But it's basically pushing on that. A horizontal shrink is the same thing as a vertical stretch. Essentially, it's not exactly the same thing, but it has the same changing of the shape as a vertical stretch does, which means I drew this thing wrong. In other words, the horizontal shrink is going to end up looking like that. That's what a vertical stretch would look like. That's what a horizontal shrink is going to look like. And if this number inside the function is between 0 and 1, then it's a horizontal stretch. So just remember that the stretch, the horizontal stretch and the vertical stretch are determined differently. One has to be greater than 1 and the other has to be between 0 and 1.
All right. So let's just say that it was log to the 1/4 of x. Would that be just the same thing but in the opposite direction?
Horizontal stretch.
Okay.
There's only two things. There's shrinks and stretches. I mean, there's shifts also, but the only two things that change the shape of the curve are shrinks and stretches. And whether it is a shrink or a stretch depends totally on whether it's greater than 1 or between 0 and 1. And if you start with the vertical one makes sense. When it's greater than 1, it's a stretch. That's the one to memorize, and just know that horizontally it's the opposite of that.
Okay. Yeah, that I understand that then. That works. Okay.
I'm looking at some of these others here. Okay. Let's talk about expanding logs. Let's look at 25.
All right.
You're going to have to expand and condense.
Okay.
Just as equally.
All right. So then, to expand a log.
Expand that one right there.
So is that log base 3 of 6 plus log base 3 of x plus log base 3 of y?
And these bases have to be the same. If you don't have same base, you can't do anything with any of this. In other words, if this was a base 5, I would not be able to condense that back to what I started with. Now, sometimes you can do more with that. But How would you get that number off of a calculator? Log base 3 of 6.
Since all you can do on a calculator with like just the log and the ln button is 10 and
right. So how do you get an oddball base on your calculator?
The log
change of base formula. Okay, what does it become?
Log base.
Believe it or not, the base does not matter. What that becomes is log of the bigger number. I don't mean larger, I mean the higher, the one that's closer to the top, divided by the log of the base. And this can be common log, it can be natural log, it can be log base 17. All of these are the same, believe it or not. It seems a little strange, but they are. That's the same.
Okay.
So when you use the change of base formula, it doesn't really matter whether you change it into common log or natural log. Either one of them you're going to be able to get out of your calculator. And if they wanted you to turn that into a number, that's what you'd have to do, is use that change of base formula. But I don't think you'd lose points if you left it like this. Now, let's say that instead of a 6, that was a 9, and now this was a 9. Now you might lose points if you left it like that, because that becomes 2.
Just 2?
Yeah. In other words, evaluating that expression, 3 to what power is equal to 9? Well, it's 2.
Oh, okay.
Okay.
That works.
All right. And when you can turn it into a whole number like 2 or 1 or 0, you probably should.
Okay.
Let's look at 28. I'll write it. Log of x to the 5th, y to the minus 2, divided by 2y.
Okay. So then that would be log of x to the 5th plus log of y to the negative 2 minus log to the, or log of 2 minus log of y.
Do I need parentheses?
Around the 2y.
No, I don't.
No?
Not if I'm going to do it like that. In other words, if I was going to use parentheses, then this would have to be plus. Okay? In other words, you are dividing the numerator by both of these things.
Okay.
Now, there's one last thing you have to do to fully expand this. What is it?
Beyond this.
Take the exponent and put it down in front of the log. And that's perhaps the greatest attribute of logs, is the fact that, because when you're solving if your variable's in the exponent, being able to do this allows you to turn it into an algebraic expression. You see what I'm doing?
Yeah.
And notice that this one just turned into negative, and I could have made it negative the whole time. In other words, the moment I saw that minus 2, I could have put that y in the denominator, and in fact, let's do it, because I think it actually turns the problem a little bit. Oh, yeah, no, we can still solve it. Can I do anything more with this thing?
With this right now? Did you do anything with the minus log 2?
Well, not really, because it's base 10. So I don't, 10 to what exponent equals 2? That's going to be an irrational number, so we just leave it as log of 2. But here, I can do something with these two, that one and that one. If you think of the log of y, as being an apple, well, I got minus 1 apple and minus 2 apples. That's minus 3 apples. So I
Okay.
take that log and just up this by one number. Okay? And notice that I could have done this problem a number of ways. I could have combined the y's to start with. In other words, I know that that y to the negative 2 is the same as being on the other side of the fraction bar to the positive 2. And in fact, then the whole thing turns into y cubed. And now, when I go to expand that, I immediately get that.
All right. Yeah.
So you can do these things in different paths and still get the same answer.
All right.
It's this first thing up here, I'm glad we did it that other way, because when you're dividing by two things that are multiplying each other, you have to be real careful not to put parentheses. If I put parentheses around that, that's different. That's not the same thing now. In order for it to be the same thing, I would have to add. And one way you can think of that is this negative sign in the parentheses means that I'm subtracting whatever's inside the parentheses, and they're being added because they're both in the denominator, multiplying one another. So lots of different ways to look at this. But at some point you need to remove those parentheses. And so why put them in the first place? Just notice that it's minus and minus because they're both in the denominator.
All right.
Let's condense some. Let's go the other way here.
Okay.
Turn this into a single log expression.
Okay, so then with this, would you, well, the first thing would be that it would become ln3 squared minus...
Yeah, that's probably the best first step, is to take any leading coefficient and turn it into an exponent. In other words, basically you're doing the reverse of the other. That's the first step. Now what?
Now would you do, would it be ln or 3 squared divided by 5?
And that's the argument. And then one last thing you can certainly do is square 3 and turn that into a 9. So you're really taking the natural log of 9/5.
Okay.
Okay. Another thing, good thing to know is that when you take the logs of numbers greater than 1, you get positive. When you take the logs of numbers between 0 and 1, you get negatives. In other words, all logs look like that. That point being 1, comma 0. So if I take a log somewhere in here, it's going to be negative. If I take a log somewhere out there, it's going to be positive. What this tells you is that if I were to take the log of 0.00000001, I'm going to have a huge negative number because it's headed towards negative infinity. Closer I get to 0, the closer I'm going to get to negative infinity on the log chart. And that's why you cannot take the log of 0. Taking the log of 0 violates the domain. Oh, and they had some domain. No, they didn't. But let's talk about domain. If I say the log of x, y is equal to the log of x, what's the domain of that function?
What's the domain?
This one right here.
0 to infinity?
Correct. Infinity has a parentheses. What about the 0?
The 0 has one as well.
Okay, good. Whereas if I say, what's the domain of this? Y equals square root of x. That is bracket 0 to infinity. In other words, you can take the square root of 0. And what the thing to take away from that is that the domain restrictions on the log functions are more severe than the domain restriction on the square root function. This
Okay.
can be 0 or positive. This has to be positive.
All right. I understand that function. Okay.
Let's condense another one. Let's go to 31.
All right.
Hold on, let me turn my light on to be able to see this. Okay. Let's do the first step without me rewriting it. You tell me what the very first step would be.
You would move the exponents.
Okay, so tell me what to write.
So it would be log of 4 to the 1/2.
Okay.
Log 6 squared minus log 2 squared.
Plus, now, you can distribute that leading to both terms. So let's do this in a couple steps. So I'm going to do that minus that. Okay. So that's my first step. Now, I'm going to take these leading 2's and make them exponents. So that 2 is going to go there. That 2 is going to go there. Now, what's the square root of 4?
2.
So that's the same as that. Plus log of 36 minus log of 4.
All right. And then you could condense that even further.
Yeah, go ahead.
So, since you're adding together the logs at first, you have to multiply the 36 and 2.
So 2 times 36 divided by 4.
Yeah.
And all of that becomes the log of 18. And that's your answer.
All right.
All right. Let's look at 32.
Okay.
So this is an equation. And first thing to note that it's not an algebraic equation. The difference is your exponent is the variable. I should say the variable's in the exponent. Okay?
Yeah.
So the way you solve all exponential equations is the same. And that is you need to take the logs of both sides. And you can use any log. I would always use natural log. Okay? But before we do it, we got to get rid of that leading 2. That leading 2 is not being affected by that exponent of 2x. So, in other words, before we take the logs of both sides, we want to get it isolated down to that.
Okay.
So what's the next line?
Would you have to divide both sides by 2 then to get rid of that?
Yeah. So we got 3 to the 2x equals 5/2. Now, here's where it's a little tricky. Here's the point where I've got this isolated as much as I can isolate it. Now take the logs of both sides. And which base you use doesn't really matter. You could use I would suggest using common, base 10, or base E, always. It may look like there would be an advantage of taking the log base 3. Let's examine that just for a second. Notice that if I did take log base 3, I have to do it at both sides. And this 2x, in other words, the left side immediately becomes 2x. Because remember, the log base 3 of 3 is 1, always. And the 2x goes down in front, so I got 2x times 1. So whenever you have this, log base b of b to the x, that's always equal to x. Or if it's x minus 1, it's equal to x minus 1.
Okay.
Okay.
Did you just essentially cancel each other out in that situation?
Well, your goal is to just simplify it. Now, okay, so the problem is that now my answer, I'm going to have to divide both sides by 2. So now my answer looks something like this. Log base 3 of 5 halves divided by 2. And I did that in 2 steps. In other words, 1 step to get to here and 2 steps to get to there. The problem is that I can't turn that into a number without then applying the change of base formula. So I'm going to have to turn this into the log of 5 halves divided by the log of 3, all divided by 2. You see what I'm saying? So it's not as efficient as it looks compared to the other way to do the problem, which I actually prefer, which is to just always use common log, or rather natural log. In other words, once I get it down to here, I'm going to take the natural log of both sides. Now I'm going to move the 2x down. And now that natural log of 3 is just a number, so I'm going to divide both sides by 2 times natural log of 3.
Okay.
And that is what x is equal to. And it appeared like maybe it was an extra step, but you got to make that extra step regardless, whether you started off taking log base 3 or using natural log. So I don't even deal with those bases that aren't 10 or E. Not unless I have to. In other words, if they've given me a problem and it's in base 3, then I got to stay in base 3. But when you're solving an exponential equation and you have your choice of, you can use any log you want to take the log of both sides, I always use natural log.
All right. Okay. Cool.
Solve the equation, check for extraneous solutions. Yeah, you know what extraneous solutions mean, right?
Yeah.
In other words, let me give you an equation. Let me give you a really good example of I think that'll work. Solve this equation.
Okay. So then the first thing you'd have to do is condense, right?
Correct. Turn the left side into a single log expression.
All right. So then that would be log of x squared plus x equals 3.
Okay. Now turn that into an exponential. expression.
All right, so then that would become,
you know what? I don't want that number to be 3. I want it to be, just let me think for a second, 1. Let's make that number 1.
okay.
Now turn it into an exponential expression.
All right, so then that would become,
Always start, whenever you're trying to turn a log expression into an exponential expression, I have a real easy way of doing it, assuming the log is on the left side of the equation, and that's take that number, raise it to that power, and it's equal whatever's in the middle. So this would be 10 to the 1 equals x squared plus x.
Yep.
Okay. Now we got to solve this quadratic, but it's a simple quadratic. Okay. So we get this equals 0. Just trying to figure out how to come up with a number that factored nicely. For sake of this argument, let's make this 12. Okay? And I could do that easily by just making these all base 12.
Yep.
Now it would be 12 to the 1 equals x squared plus x, and then I move the 12 over, and then that factors into what?
X plus 3 and x minus 4?
The other way. The bigger factor always has to go with the sign that's in the middle.
Oh, okay, so then x plus 4 and x minus 3?
Yeah. Now, notice log equations frequently give you extraneous solutions. In fact, the 3 things that consistently give you extraneous solutions are radical signs, logs, and absolute values. If you're solving any equation that uses any of those, then always keep a keen eye out open for extraneous solutions. First of all, what are my 2 solutions?
-4 and 3?
Notice that when I go to check -4, I'm violating the domain.
Mm-hmm.
And in other words, I have to go up there to check. I can't plug in -4 for x because I'd be taking the log of a negative number here and also the log of a negative number there. 3 works. 3 would work nicely, but not -4. And notice one other very, very interesting thing. This is base 12. And that is that they would both pass inspection if I tried plugging them in there. Because -4 squared is 16, minus 4, 12, that becomes a positive number. Mm-hmm. So you can never check except the problem you were given. And the problem you were given was this one at the top. You always have to check your solutions there to see whether you violate domains or not. And you almost always do, because when you're solving these quadratics, you end up with a positive and a negative number, and negative numbers aren't going to do so well in most of these log expressions. But it's real peculiar. It's always seemed very peculiar to me that even though they teach you that line 1 is the same as line 2, they're not precisely the same. Notice. In other words, when I condense this to this, I cannot use this one to check my domain restrictions. They both work. They both work in that one, but they don't both work up there. And what that tells you is these 2 expressions are not exactly the same. It's a nice little technique for solving log problems, this condensing and expanding, but don't get confused into thinking that this is exactly the same as that. And it would be easy to do so. You know, usually when you work through any algebra equation, line 2 is the same as line 1. It may have been manipulated, but it's the same. Well, not here. Not with logs.
Okay.
All right. That's probably a good place to end. Did you guys cover the logistic growth function?
No, we didn't. She only got us up to
I was
8.6.
going to say that's good. That is a different function. That's a different elementary function. That's not one of your 10 elementary functions that you've studied in math. It's a whole new one. In other words, you can't get a logistic function by transforming one of your 10 elementary functions. You can get an awful lot of functions by those 6 transformations, but you cannot produce a logistic function. It's its own function in its own right.
Okay.
All right, Morgan, I am going to let you go.
All right. Awesome. Thank you so much.
I think you're in pretty good shape. I think you'll do fine on the test.
All right. I sure hope so.
Okay. Talk to you later.
All right. Thank you again. Bye-bye.